Yeah, I'll just talk about, actually, James Very just gave a wonderful introduction to what I'm going to talk about. And it does follow on what Professor Mitra, a great scientist, worked on. And that's QCD at the amplitude level, factorization theorems, counting rules, the front form light front theory, the application of nuclear amplitudes. He was at SLAC in the early days, and he worked on things that I worked on with Ben Chertok. So I got to know him then. And so that's wonderful. So he also worked on the spin dynamics of the three-quark wave function in light front theory. So he worked on that. It follows on the light front follows on the work of Dirac. We heard James Very talk about this. This is way back to 1949. Dirac had showed, in fact, that if you use the front form, that is light front time, tau equals t plus z over c, then in fact all the answers are causal and boost invariant. So it doesn't depend. None of the observables depend on the frame of the rest frame of the observer. So everything is really Lorentz invariance and causal. So even, in ordinary equal time, you don't even have causality. So the famous formula is the Dirac front form, where in fact the form factor is just the overlap of light front wave functions. The light front wave functions are functions in momentum space of the x variables. That's the k plus over p pluses, the k perps, the transverse momentum, and the spin projections of each hadron. And they add up with the right sum rules, in fact, to the momentum of the hadron. The sum of the x is 1, and the sum of the k perps is the transverse momentum of the hadron, or 0. And the case of the helicities as well. So everything's invariant under boost and independent of the momentum of the hadron as well. So the form factor is just the overlap of two light front wave functions, and we heard about this. If you know the wave function, psi of x and k perps on one side, and you know the other wave function in the final state, then you can compute all the form factors, every one of them. And in fact, it goes on and on. You can actually, Larse and Pasquini showed, in fact, that if you know the light front wave functions, you can evaluate the overlap and get virtually every observable exclusive variable, inclusive variable. You get factorization theorems, you get de Glapp evolution, herbal evolution for exclusive processes, and all the factorization theorems. If Lepage and I use that formula to prove the exclusive process perturbing QCD, we define what's called the distribution amplitude, which is the integral of the transverse momentum of the valence state. That has much of the physics of each hadron. And you get a rigorous QCD analysis of exclusive processes. You get the hadron distributions and what's called the herbal Efremov-Radushkin Brodsky Lepage evolution equations. And if you start with the Lagrangian of QCD, you can systematically derive the Hamiltonian of QCD, but in front form time. And the light front Hamiltonian is the sum of the kinetic energies, which is m squared plus k perp squared over x, plus all the interaction terms. And you can get a complete description of QCD in principle from this by diagonalizing the light front Hamiltonian. And if you diagonalize that light front Hamiltonian, you get all the hadron masses, every one of them. And the eigenvalues are not energies, but the invariant mass squared of each hadron. And then the projection on the free Fock basis is, in fact, the light front wave functions I just described and James described as the description of all the hadrons in terms of their Fock space. And when you use this, you get all the counting rules. You get the core counting rules that they goes a power 1 minus x, just to the twice the number of spectators minus 1 as you go to large x. You get the form factors at large q squared, that 1 over q squared to the number of constituents minus 1. You get all the hard exclusive reactions, pp scattering and so on. And just by counting the number of particles, active particles, you get the leading power. And you get the same thing for inclusive processes. You get all the counting rules at large x and so on. Now my own slide is not moving. All right. Oops. So the one way to deal with this is to actually diagonalize the matrix. And I originally started this with Hornbostel and Pauli, and now we have, in fact, this wonderful work on basis light front quantization by James Very. So what you do is you write down a complete momentum space description of all the Fock states, and in principle, you can diagonalize the light front Hamiltonian and get all the eigenvalues. In practice, you're limited by just the size of the matrices. You actually, the trick is to use actually a simple momentum space representation, which is really discrete. And then you can give this to the computer, and you can diagonalize that light front Hamiltonian. And what you're doing is using periodic or anti-periodic boundary conditions. So then you derive all the counting rules and so on, and you get fantastic results. In the case of James showed lots of different results. In fact, you can get from this, including if you can actually get the complete quark-gonium spectrum. You also derive the counting rules, and for example, PP to PP, the differential cross-section goes like a function of angle over s to the 10th, and that works to remarkably well over many angles. And you also get what's called spin exchange. That is, you can exchange, if you do K plus P, you get the right answer by just exchanging an up quark, and you get the interchange amplitude, which gives you the basic angular distribution, 1 over u, 1 over t squared, of the matrix amplitudes. So the challenge for all of us now is to compute hadron structure, spectroscopy, and the dynamics from QCD itself. And you want to have color confinement. We heard about that. You want to understand the origin of the QCD mass scales. You want to understand meson and baryon spectroscopy. You want to understand exotic states like tetraquarks, pentaquarks, gluonium, of course. And then the fact that actually all the slopes of Regge behavior are universal in both N and L. The meson trajectories and the baryon trajectory, Regge trajectories, if you go up to large S at fixed T, all the slopes are the same. How do you explain that? You also get an almost massless pion. If you have a zero mass input quarks, you get a zero mass pion. That's remarkable too. That gives you the Gell-Mann chiral symmetry breaking. And also you want to derive the QCD coupling at all scales, not just at large momentum where you see the asymptotic freedom and so on. You also want to eliminate scale uncertainties and scheme dependence. And you can do this with what's called the BLM or PMC. That's the principal maximum conformality. There's a field of that. So we were looking for a first approximation to QCD, which is comparable in simplicity to Schrödinger theory in atomic physics. It's relativistic, frame independent, color confining. And you want to understand the origin of the hadron mass scale, even if the quark masses are zero. And the new approach that I'm going to talk a little bit about was done with Dash and Dorsey and de Terman, and that is using what's called anti-de Sitter space QCD light front holography. Holography is because we're actually using one additional space-time dimension in an ingenious way. So you start with the exact light front Hamiltonian, which has got the kinetic energy terms. That's the K perp squares plus m squares over x's. And then all the interactions, one gluon and so on, exchange. And you get this wonderful light front Hamiltonian, which is in principle solvable, but very difficult to solve. So instead, one's using, in fact, a trick, which is called light front holography, where in fact you replace, in the case of a two-body, two-particle equation, that could be quark anti-quark, or in the case of baryons, quark diquark, you can actually get a potential, which actually is written as U of zeta. And that unfortunately, you don't have it in front of you, but I have it here. And that is, you introduce a variable zeta where zeta squared for, say, a pion or a meson is x times 1 minus x, the light front constituents, times b perp squared. That variable is remarkable because zeta squared is actually the key variable to hadron physics once you study it, because it's really what you get as an effective two-particle equation when you reduce all the higher Fock states. The actual key variable is the zeta squared. Again, x1 minus x times b perp squared. And then you get a light front Schrödinger equation, which goes like d by d zeta squared. That's the light front kinetic energy. It's equivalent to k perp squared over x1 minus x. And then there's an angular momentum term, which is 1 minus 4 alpha squared over 4 zeta squared. That's the usual orbital momentum term that you know in non-relativistic physics, but it's now completely covariant and frame independent. And then a potential U of zeta. And the U of zeta turns out from this light front holography to have an amazing simple form. It's kappa to the 4 zeta squared. It's like a harmonic oscillator. So again, zeta is the critical variable, a to x1 minus x b perp squared. And there's an extra term, 2 kappa squared L plus S minus 1, which just comes from kinematics. This equation, which is just a simple two-body equation with the variable zeta squared, is, again, U of zeta, the potential is kappa 4 zeta squared plus the kinetic energy term. That automatically gives the complete two-body spectrum. This is something I showed with de Terman, Dash, and Lorsay. It's rather remarkable. And what you're doing is you're eliminating the higher Fock states, all the retarded interactions, and so on. You're getting remarkable simplicity with this one potential. If you like, it's a semi-classical first approximation of QCD. So you get this light front Schrödinger equation. Again, it's minus d by d zeta squared. That's for massless quarks. That's k perf squared over x1 minus x. And then 1 minus 4L squared over 4 zeta squared. That's the orbital momentum. And then this amazing potential, which is confining, u of zeta, which is kappa the 4 zeta squared, and then an extra kinematic term, 2 kappa squared L plus S minus 1. Now, if you the because we're scale invariant, actually the units are not specified. But if you pick in our units, kappa equals 0.5 GeV, it really reproduces the entire hadron spectrum. It's rather remarkable how it works. There's work by D'Alfa, Fubini, and Furlan, and Fubini and Bervinci, which is similar. So the first thing you look at is the Regge spectrum. Out of this confining potential, this simple one-body equation, you get the whole meson spectrum, and it's linear in L, it's a Regge spectrum. And then you get the baryons, which are quark diquarks, and they're exactly the same answer. The same slope is exactly the same in terms of kappa half of GeV. So you get exactly m squared linear and 4 kappa squared. And you get the same slope in both n, the principal quantum number, and the orbital momentum. And you get the same result for both mesons and baryons. The only difference is that in the case of the mesons, the spectrum is 4 kappa squared times n plus L meson. That is the orbital momentum in the mesons. And in the case of the baryons, it's 4 kappa squared and n plus LB plus 1, where LB is the orbital momentum between the quark and the diquark. So this is exactly what you see in nature. You see the pi n trajectory, the pi B1, pi 2, B3, pi 4, and so on, B5, exactly parallel with the proton, which starts out 940 and then goes up to the 1520, the 1680, and so on. So you get the universality of Regge slopes, both not just in L, but in N as well, exactly the same slope. And if you make this one shift of the orbital momentum of the mesons compared to the baryon by 1 unit, then you see, in fact, that the meson spectrum and the baryon spectrum fall right on top of each other. That is the rho spectrum, the rho omega spectrum, and its Regge recurrences exactly duplicates the delta trajectory. That's rather remarkable. And that's a kind of supersymmetry, because what you're doing is actually relating mesons with baryons, bosons with fermions, and they have exactly the same mass. And this works experimentally to very high accuracy. So there's a hidden supersymmetry in QCD between mesons and baryons. The mesons are quark antiquark, the baryons are quark diquark. And that's rather remarkable how that works. And if you go back to the heavy quarkonium, which is what James Very did with the same potential, harmonic oscillator potential, you reproduce basically the whole heavy quarkonium spectrum. So where does this all come from? It's actually what's called a dilaton modified anti-de Sitter space. And what happens is if you start with the action as e to the phi of z, and then r squared over z squared, and then the normal kinematic dilaton in the 5th dimension, you actually see that, in fact, if you pick e to the phi of z, the prefactor, as e to the plus kappa squared z squared, it gives you exactly what I spoke about before. And in fact, it's really an example of what David Gross called a duality of QCD with string theory. That is, you go to one extra dimension in 5th dimension, and that one extra dimension in z reproduces, in fact, everything I said in zeta in our world. So you take this action in the 5th dimension, and you can map it exactly into our world. Klebanov and Baldacci did something very similar. And what happens is you get then this remarkable result that the 5th dimension has a potential, has a behavior, an action prefactor, which is e to the plus kappa squared z squared. This is what I did with Gita Taraman originally. And when you then realize that the variable z in the 5th dimension is this variable zeta in our world in 3 plus 1, the var zeta is actually, zeta squared is x1 minus xb perp squared, then you reproduce this simple one-dimensional light front equation, which represents the entire meson spectrum, as well as the baryon spectrum, if you realize that the baryons are really quark-diquark structures. And again, it reproduces the entire hadron spectrum with Regge trajectories, universal trajectories in N and L and baryons. And then if you take those solutions, you get the eigenfunctions. The eigenmasses are the m squareds. The eigenfunctions are the light front variables. And you can then calculate then the psi of x and k perp squared exactly from this potential, from this simple one-dimensional light front equation, and then use the Drell-Yan-West formula to compute form factors. And what happens is you can use what's called a Soper formula, in fact, which allows you to integrate one variable out, and you actually get very simple results for form factors, analytic formulas in terms of the K1 Bessel function. So you get this remarkable ingredients. So you get the fact that the wave functions in the fifth dimension angle variable, which we call variable z, is exactly the same wave function in physical space, but in the terms of the variable, the wave functions are all in functions of zeta, where zeta is the square root of x1 minus x b perp squared. And so this gives you the light front wave functions, and you actually understand it for all n, all orbital momentum, internal orbital momentum, and so on. So this is actually a remarkable advance, I think, that in physics. And this is called light front holography. It originates from this anti-de Sitter space model of softwall QCD. And you get this, again, one-dimensional equation with one variable, kappa, which is 0.5 GeV. And that reproduces all the hadron masses. And then you can put heavy quark, that's for light quarks. For heavy quarks, you put in the phenomenological heavy quark masses. So all the ratios of masses are determined. The value of the proton mass, so depends on kappa, but that's because we use our GeV convention. So you get beautiful equations for mesons and baryons, eigenvalue equations, which are identical for mesons and baryons. The only thing they differ by is the internal momentum is 1 unit difference. So you again find this meson-baryon degeneracy where the mesons are superpartners of the baryons. And we've checked this out throughout the entire spectroscopy. This is work with Dash and Norsay. And you go through this and you get these beautiful Regge formulas and formulas for light front wave functions, which agree with phenomenology, the form factors. In the case of the pion, you get a zero mass pion if there's no input quark masses. That's one of the solutions. And you get the complete spectrum. The m squared is equal to 4 kappa squared times the quantity n plus j plus L over 2. And that really is textbook. This is actually just like hydrogen physics in atomic physics. And you also get the analytic form for the light front wave functions. You also see a superconformal algebra. This is mesons, which are quark antiquarks with baryons, and the tetraquarks. And you get so you go from mesons to baryons, and from the baryons, you can replace from the quark diquark, you replace the quark with another diquark, and now you get two diquarks, and that's the four quark systems, which are the diquarks. So then you go back and you see, in fact, the universal Regge behaviors, and you can also get the tetraquark spectrum, as well as the light front wave functions and the massless pion and all the things I talked about. And you get this superconformal algebra, which relates mesons to baryons to tetraquarks. And you get universal behavior in the kinetic energy terms, universal behavior in the potential, and so on. And there's a very old theorem. So supersymmetry, which is built in between the meson-baryon spectra, has really been a hidden symmetry of color SU3 in physics. You don't need squarks or gluinos. It emerges from this light front holography and color confinement. And you get beautiful Regge spectrum, as I said, degenerate behaviors between the rho omega trajectory and the baryon trajectories. The whole formalism is relativistic, frame independent. The QCD mass scale appears with a unique light front potential. You get the spectroscopy dynamics of light quark hadrons with one parameter. You get the zero mass pion. You get the universal Regge slopes in N and L for both mesons and baryons. And you get the same splitting, this parallel trajectories. You don't actually, some people think that you get a breakdown of chiral symmetry at high momentum. It doesn't break down. You just see this, it goes on. And you get the phenomenology of light front wave functions, form factors, all the electroproduction exclusive processes, and you can extend it to heavy quarks. So the underlying principles is number one, Poincare invariance. You're independent of the observer's Lorentz frame because you're quantizing, like Dirac said, fixed light front time tau. You have causality, information only within the causal horizon. That's light front physics. And again, I emphasize that instant form violates causality. Light front holography, where you have this amazing resemblance between the fifth dimension physics of ADS5 in the variable z in the fifth dimension with the variable zeta in our world, where zeta squared is b perf squared x1 minus x. You have a mass scale kappa, which is the only way you break conformal invariance of the action. You have a dilaton in the fifth dimension, e to the plus kappa squared z squared, which is the color confining potential in our world. U of zeta squared is kappa 4 zeta squared. And you get the superconformal algebra, which relates mesons to baryons, which are quark diquarks, and tetraquarks, which are diquark antidiquarks. And if you look again at all the different theories, you see, in fact, the data is universal slopes in N and L, and you get beautiful light front wave functions, which have, if you go in N, you see the wave function crosses 0 N times, and so on. So you understand the wave functions and beautiful results for it. And you also get the distribution amplitudes and light front wave functions. So yes, am I about through now? I'm not watching my time.
Yes.
Can you
You
hear me?
have 5 more minutes.
Okay, yes. So you get light front wave functions, which actually have a very simple form, and distribution amplitudes. The distribution amplitude for the pion, for example, is just 4 over root 3 pi times f pi, the pion decay constant, times root x1 minus x. And that reproduces virtually everything we know about mesons. It's rather startling how simple this is. And the value of f pi, the pion decay constant, is related to kappa through the formulas. The light front wave function itself is a Gaussian in k perp. It's e to the minus k perp squared over x1 minus x with a factor 2 kappa squared downstairs, and an overall factor 4 pi over kappa root x1 minus x. So this is really remarkable. You get one of the things that's very beautiful is Forshaw and Sandepan use the holographic light front wave function for the rho meson to calculate diffractive rho electroproduction. And remarkably, the description that you get for the diffractive rho electroproduction cross-section just goes right through every data point. It's rather remarkable. And you get sigma L over sigma T because you can vary in the case of the cross-section, you can vary the virtual photon polarization and get the ratio of L over T. And all this comes just from one light front wave function, which is psi of x and k perp is 4 pi over kappa root x1 minus x times a Gaussian in k perp squared over 2 kappa squared x1 minus x. That one wave function is the solution. It's a lot analogous to the Bohr theory of atomic physics, where you get so much from just a simple ordinary Schrödinger equation. Here we have the light front wave function equation. And we get these beautiful light front wave functions, and which actually not only work in the initial state, but in the final state. And so this allows you to compute hadronization at the amplitude level. So when you produce a jet, and so in the quark and antiquark produce a meson, the light front wave function actually gives you, in fact, the hadronization probability at the amplitude level. And everything's boost invariant. You're connecting the confined quarks and gluons to hadrons. So again, just as a summary, we have a theory which has got color confinement, and we have the analytic form of the confinement potential. You have all the conformal properties of QCD built in despite the mass scale. You have a massless quark-antiquark pion bound in the chiral limit. You have QCD coupling at all scales. I didn't discuss this, but you actually describe what we know from phenomenology, the QCD coupling alpha strong at all Q squared, all space like Q squared. And that comes from what's called the Bjorkian sum rule, where you actually measure directly the QCD coupling at all scales. And then you have the connection between perturbative and unperturbative mass scales, everything Poincare invariant. You get the hadron spectra, Regge trajectories with universal slopes in N and L. You get supersymmetric fourplets, meson baryons, and tetraquark supersymmetry. You have their light front wave functions, form factors, structure functions, hadron observables. All the counting rules are obeyed. You get hadronization at the amplitude level as the quark jets and gluon jets become hadrons, many phenomenological tests, and it's systematically improvable with the basis light front quantization, and that's using the methods that James Very and his group discussed. So this is really a remarkable supersymmetric features of hadron physics. And again, if you look at the data, you see that in the strangest sector that the kaon and lambdas, the kaon mesons and the lambda baryons are degenerate. If you plot this amazing thing, but relation between LM and LB just by 1 unit. And it works for the D mesons and the lambda C mesons in the case of the charm sector. That works perfectly. And you get the tetraquark spectrum right, and you get superconformal algebra. You get the structure of the F2, delta, and A1 meson all together as a superconformal fourplet. And that's, again, tetraquark physics. So you have superconformal meson baryon tetraquark symmetry, which is gorgeous and comes from all one masterful equation. And if Marina Nielsen did a heroic job, she went through the whole particle data book spectrum, and she looked at the meson baryon tetraquark and saw that, in fact, you can organize the whole hadron spectrum using this formalism I just discussed. And with the super partners, also with one charm quark, everything works beautifully. Beautiful agreement. So you also have all the tetraquarks and how they line up as Reggie trajectories. That's very beautiful. You have a harmonic oscillator potential capital 4 zeta squared. But if you go to heavy quarks, two heavy quarks, it becomes just constant times r. So in fact, this capital 4 zeta squared in 3+1 physics is in fact the same as the linear potential we're familiar with for heavy quarks. This is work that Travinsky, Gwasik, Dash, and Determan and I did. So again, you get these light front wave functions. They're invariant or boosts. There's remarkable insights from ADS QCD. You get all the form factors just from the overlap of light front wave functions. And you get, if you plot q squared times f pi, it goes right through the data. If you look at the time-like, you can actually understand the time-like structure as well from the pole structure on the time-like side. And that works very well too. And you see, in fact, the combination of the twist 2 and twist 4 contributions to the meson, and there's a 14. The fit shows it's a 14% probability for the 4 quarks in the meson pion. And you can plot the meson and baryon the time-like and space-like form factor together, get one universal picture which unifies the JLab data on the space-like and the Babar data for the time-like pion form factor. And for the case of the baryon form factors, you get q to the 4th times f1. The Dirac form factor is constant. You see that right for the protons. But one thing that's very unusual that we're still puzzled by, you get the neutron Pauli form factor dead on, but the Dirac form factor is off. The points around q squared of 4 j squared are too low experimentally. And that's about the only place where you see a radical departure from the prediction. So people should redo that experiment. That is the Dirac form factor of the elastic neutron proton form factor. And there's a beautiful formula for the Pauli form factor, overlap of light front wave functions, where you get a spin difference between SC equals -1/2 and SC to the +1/2, SC to the -1/2 in the initial state, SC to +1/2 in the final state. And you actually derive the non-zero proton anomalous moment and its internal non-zero orbital momentum that comes from this physics. And you get this, again, the Pauli form factors and so on. And then, as I mentioned before, if you use the Bjorkian sum rule, which is the integral over x of the G1 inclusive structure function to spin-dependent structure function, that integral gives you 1 minus alpha G1 of q squared. It gives you a definition of the QCD coupling at all q squared. It's well measured, has asymptotic freedom at large q squared, computable at large q squared, perturbed QCD. It's got the universal beta 0, beta 1, which is a theorem, and you get analytic connections to other schemes and what's called commensurate scale relations. And then if you look at the data for the Bjorkian sum rule running coupling, alpha strong, it actually looks just like the data. At low q squared, in fact, it's besides asymptotic freedom at large q squared, at low momentum, the running coupling is pi times an exponential minus q squared over 4 kappa squared, where again, kappa is that universal mass scale I introduced before. And if you look at this, you see a beautiful transition between the space-like, the low q squared and high q squared QCD coupling. You know, we always talk about asymptotic freedom. We rarely talk about the low q squared dependence of alpha strong, and it's just a Gaussian, either minus q squared or 4 kappa squared. And the Gaussian matches the perturbative QCD at a Q0 of 0.87 GeV, plus or minus 0.08. So I think I've talked way too long. I'm sorry I didn't show the slides. It's really terrible. But you see, in fact, the distribution of the quarks and the proton. I have slides on that. The U quark, the D quark, the polarization contributions, and so on. I think it's really remarkable that you get so much from this very simple holographic light front QCD. And I'll stop right there. So I'm very happy that I could speak at this in honor of A.N. Mitra, his memorial symposium, and I'm glad I could meet him, and I think he would be very much like the content of my talk today. Okay, thank you. I'm happy to take questions.
Thank you,
And
Prof.
I apologize that I gave it all orally. Yeah, I don't know if it's sensible or not. Who knows? Do you want to comment?
Thank you, Professor Stan, for very, very interesting and enlightening talk. So maybe
Thank
we
you.
can have only one question.
Hi.
Yes, Professor Kaushal.
Here, R.S. Kaushal from the Delhi University, Professor Brodsky.
Good to meet you.
Yeah. Some time back, there were speculations about pentaquark baryons and tetraquark mesons. There were speculations about pentaquark baryons and tetraquark mesons.
Oh, the pentaquark mesons, is that what you said?
Baryons,
yes.
Yeah. Pentaquark baryon, yeah. So what the current status?
Yeah, so experimentally, there's, we use the data that's in the particle data book to identify all the tetraquarks. And you're asking about pentaquarks too, right?
Yeah.
And there's still more work to do that. And this, you can do things like, for example, diquark, quark bound states, and use this formalism, use this confining potential, and so on. We haven't done that, so I hope you'll look at it.
Yeah, I visited you sometime back. Yeah, if they are there, how your sum rules will work for them?
They should work. Yeah, it should work. Yes, I agree with you. That's right.
Now, is that all right, Professor Kaushal?
So please look at my.
Thank you, sir.
Because now I can see my time. It's 9:42, so we can move on. So thanks once again, Professor Stan and Professor James, for your very interesting and enlightening talk. And